Okay, so we shall carry on. We are moving into chapter 8. And chapter 8 is all about hypothesis testing. Everything builds up on previous stuff. How are we guys? How are we doing? You feel bad? After that quiz, you feel bad? Okay. Okay, so when you say you feel bad about the quiz, what in particular?
The first 4 questions.
The first 4 questions? Okay, so let's, here, let me pause this. I'm going to pause the YouTube video and I'll go over the first 4 quiz questions regarding how that goes. Okay, so we're going to move on, and are there any questions regarding, well, maybe I'll just specify just some highlights from chapter 7, okay? I just want to make sure we're all on the same page with chapter 7 before we go on, okay? So highlights and recap. Okay. I guess I should just ask, is everybody doing the homework?
Yes.
Okay. All right. So that I'm assuming you guys are telling me the truth, and you guys truly are doing the homework. And all right, is the homework useful in your learning the material?
Yes.
Okay. It should be. It should be. That's the only reason why I assign it. I don't get joy out of you doing homework, but I do get satisfaction out of you guys learning. Okay. And that's why I like my job and I like teaching this. Because I like having you guys learn, but if you aren't doing your homework, you're going to have a tough time learning. And so please do the homework, and if you face problems, you get stuck, I have those videos to help you out, or at least I've written out some answers for some of the problems, and that should at least get you pointed. The important thing is, though, if you watch the video to work through a problem, make sure you can still do the problem without the video, okay? Because everything always makes sense when you watch a video or you watch me doing a problem. It always makes sense. You say, oh yeah, I get it. But then, you know, if you feel bad that after taking that quiz, there's obviously something that you didn't quite 100% get. So, okay, so highlights from chapter 7. This was, we talked about sampling distributions. So this is just a very brief summary of chapter 7. So with sampling distributions, we know that a sample proportion p hat follows the normal distribution. Okay, so p hat comes from normal distribution, where the mean is equal to p, and the standard deviation, or the standard error, is equal to the square root of p times 1 minus p over n. Now what is p? The population proportion. Thank you. I was almost going to just quit. Okay, p is the population proportion. And so we can ask questions about p hat, such as, you know, if you take a random sample of Lego pieces, what's the probability that this random sample has this percentage blue pieces or something? Okay. We also created confidence intervals. And the confidence intervals, we would make, we can make, for example, a 95% confidence interval for P. So we're making a confidence interval about the population proportion, okay? And the lower bound is P hat minus 1.96 times the standard error. Okay, and of course 1.96, this number depends on your level of confidence. P hat plus 1.96 times the standard error. This is our upper bound. Okay, and so the lower and upper bound create an interval of plausible values of P. So based on what we see in the interval, we can make conclusions about P. So for example, maybe our interval is, 0.50 plus or minus 0.02. Okay? So then that goes from 0.48 to 0.52, and we would say I am 95% confident that P is between 0.48 and 0.52. And this would provide evidence. So this interval provides evidence that P is not 0.55 or any other value outside the interval. Whereas the interval does not provide evidence that it's not any value within the interval. It doesn't prove that it's, if somebody says, do we have evidence that P is 51%? The answer is no. It doesn't prove that it's 51%, but we can't deny the possibility that it could be 51%, because 51% is between 48 and 52. Okay? And that's what we covered in Chapter 7 last week. Okay, and I'm hoping at least all of this looks familiar. Yes? I feel like I'm pressed on time already with what I have to cover for today. So, again, any of the quizzes that you want to review, if you want to come during office hours and see your quiz and you have questions, I'm more than happy to do that during office hours, okay? So just send me an email, because I don't enjoy lugging around a giant stack of papers. So just send me an email, I would say on Monday or Tuesday. Then I'll go through my files, pull out your quizzes, and bring them to class or bring them to office hours, and I'm happy to go over them with you. Yes?
So, like how we took the quiz tonight, how long will it take for them to be graded?
So
At least we know, you're saying office hours, so we're going to wait a whole week for next Tuesday to come in?
Yeah, so I try to grade them by the weekend. I know sometimes that doesn't happen, but I'll try to get them graded and posted by the weekend, and then you can see. I mean, right now you should have a gut feeling as to whether you did okay or poorly on the quiz. And so if your gut feeling is I did poorly, then yeah, send me an email. I would say on Monday or Tuesday that says, can you bring my quiz to class or to office hours? I'll pull out your quiz out of the stack, and I'd be happy to go over it with you. Okay? Okay. Is this okay? Chapter 7. All right, so let's see. Here, let me, we'll give this another shot here. And if the volume goes crazy, well, then I'll stop. Okay. Cool. I have no. The only thing I have is this knob right here for microphone volume. All right, we'll try it like this, and we'll go. So we have hypothesis testing. This is chapter 8. Okay. So the idea behind hypothesis testing is we have a pair of hypotheses. We start off with a pair of hypotheses in mind, okay? And so I'm going to put a bunch of terminology up on the board and things. But I want you guys to, I don't know, just try to make sense of what I'm explaining here, because if it doesn't make sense, then we're in trouble, okay? So with hypothesis testing, we start off with a pair of hypotheses. Two hypotheses. We have the null hypothesis and the alternative hypothesis. Okay. The symbol for the null hypothesis is H0. The symbol for the alternative hypothesis is HA. You know what? Let me just see if changing batteries will make a difference. Testing. Well, it seems the same. I'm not sure. Okay. Okay. Both of these will have a claim. Okay. These are some kind of claim. Now, here's the key. The null hypothesis H0 always has an equal sign in it. And the alternative is identical to the null hypothesis, except the equal sign is replaced with either a not equal sign or a greater than sign or a less than sign. Okay? So the null hypothesis always has an equal sign. The alternative is identical to whatever you have in the null hypothesis, except the equal sign is replaced with not equal, greater than, or less than. Am I coming through the speakers? Is this okay? All right. And so you read a problem, okay? So we start off and we read a problem. And the problem will tell you to test for some hypothesis, okay? And it'll tell you either, test a hypothesis or claim. Or it might ask, do we have evidence that ... okay? And so as you read the problem, there's going to be some kind of statement in there like this, and this is going to help you form your hypotheses. These statements will form the hypotheses. Okay, the rest of the problem will provide the data used to test the hypothesis. Okay. When you solve these problems, okay, you're going to calculate, there's several steps involved, but you're ultimately going to calculate a p-value to make a decision. Okay, so the new batteries isn't making a difference here. Let me, I'm just going to switch back to the old batteries. Sorry. Okay, we have a question? Was there a question?
I was just going to say that.
Okay. All right. So the rest will provide the data. Now, to solve the problem, you're going to first set up the hypotheses. Okay. And then you're going to, I would say that, this is a step in here, which is list off the data you have. That's at least a nice ringtone. So list off the data you have, and then 3, you're going to ultimately try to solve or calculate a p-value. And there are steps involved in calculating a p-value. Okay, and this will require finding your standard error. Finding a test statistic. Okay, and looking that test statistic up in a reference table. Okay, to get the p-value. And then lastly, you will make a conclusion based on the p-value. Okay, so I'm starting off with kind of just what you're supposed to do while you guys have no idea what a p-value is and what all of this stuff is. Or maybe you guys already know. But let me explain that, and I'm hoping this will make sense. Okay. So here's a. Let's say there's a new game in Las Vegas. Well, let me just make sure you guys have this all written down. Okay. Well, anyway, let's say there's a new game in Vegas, and it's a silly game. It's casino coin flip. Okay. Maybe to make sure that they get money, it costs $1.05 to play or something. Okay. And you just say, I think it's gonna land heads, and if it lands heads, you win $1, and if it lands tails, they keep your money that you put down. Okay. So what's the probability you should win the game? Every time you play, you should have a 0.5 probability of winning, right? Okay, let's say you play the game 10 times. And if you play the game 10 times, how many times should you win? You should win around 5 times, right? Let's say you win 7 times. Okay? So you've won 7 times out of 10. Does this mean you're cheating? Okay? Or let's say you're running the casino and you're watching someone and they played the game 10 times. You're expecting them to win 5 times because it's a coin flip game, but they end up winning 7 times. Would you accuse that person of cheating?
No.
No, why not?
It's within the margin.
Well, so basically, they are winning, quote, more than what we would expect, but winning 7 games out of 10 doesn't seem that weird, okay? It seems pretty reasonable, okay? On the other hand, let's say someone played 1,000 games, okay? They won 1,000 games. How many times would you expect them to win? You would expect them to win 500 times. Let's say they won 700 times. Okay, so that's 70% winning. Same as 7 out of 10, but this time they won 700 games out of 1,000. Do you think this person is cheating? Yeah, okay, so they've won 200 games more than what you would expect at 500. So would you does it seem like this person's cheating? It seems like it, right? Okay. Or, you know, if we were to just change the numbers around and we say some guy played 10 games and he won 8 games out of 10, would you think he's cheating? No, you'd just say, oh, you got really lucky, okay? On the other hand, if somebody played 1,000 games and they won 800 games out of 1,000, do you think this guy's cheating? Yeah, it seems pretty clear that we don't know exactly what's happening, but the fact that he won 800 games out of 1,000 feels like he's cheating, okay? Now, is it possible? Is it possible that the guy was actually just really lucky and won 800 games out of 1,000? Is that technically possible? Technically, it's possible, but in our intuition, we feel like, yeah, technically you could get 800 wins out of 1,000 playing fairly, but it seems like that is so unlikely that I'm ready to conclude that you're cheating, right? And I think if we do the math, winning 800 games out of 1,000 is like, you know, you have less than a 1 in a million chance of that happening. It's probably like 1 in a 10 million chance of that somebody will win 800 games out of 1,000. Okay, and so technically the guy could, you know, let's say you confront him and say, I think you're cheating because you won 800 games out of 1,000, and you could say, no, I'm not cheating. I just got really lucky. Now, he could be telling the truth, but then the probability, then you'd have to calculate, well, if you are telling the truth and you are playing the game fairly, what's the probability that you actually win, that a person playing fairly wins 800 games out of 1,000? And if that probability turns out to be like 1 in a billion, then what does that tell you? So it doesn't, you have to make a choice, okay? There's 2 possibilities. He's either that lucky, 1 in a billion, or he's doing something like cheating, okay? Now, I would say at that point, if it's 1 in a billion versus he's cheating, we would say, okay, well, the more likely situation is that he's cheating, okay? On the other hand, if a person plays 10 games and wins 8 games out of 10, should we confront the guy about cheating? 8 out of 10 is 80% wins, which is a lot more than 50%. But what's going on there? In that case, we could accuse someone of cheating for winning 8 games out of 10, but their defense would be, no, I just got lucky. And then we could do the math and say, okay, well, if you are playing fairly, what's the probability that a person playing fairly wins 8 games out of 10? And what do you think that answer is? Okay, it's not huge. Not everybody's going to win 8 games out of 10, but maybe it's like 8% or 9%, okay? maybe there's a 9% chance that a person playing fairly will win 8 games out of 10. Okay? So if there's a 9% chance that a person playing the game fairly will win 8 games out of 10, then do you think we should accuse the person of cheating? No, because that means you would be accusing 9% of all fair patrons to your casino of cheating, okay? If that's what would be going on, okay? And so there's basically a non-negligible probability that this guy is playing fairly and just happened to get lucky and win 8 games out of 10. And that's essentially what we're doing in hypothesis testing, okay? We're going to start off with a statement, a claim, such as this person is cheating or this person is not. And then we look at our data and we're going to calculate what we call the p-value, which is what's the probability that we end up with our data if we assume the null hypothesis is true. Okay, so I'm gonna write all of this down, and but I want us to understand kind of what's going on here. Okay, and so the conclusions we made about whether the person was cheating or not was based on kind of our intuitive sense of probability. We said winning 8 out of 10 games seems like it could happen on a regular basis for fair customers. So we're not going to accuse you of cheating. On the other hand, winning 800 out of 1,000 games seems like that doesn't happen ever or very often at all. Even though it's technically possible, it seems like it shouldn't happen ever, and therefore we're going to accuse you of cheating. So let me go on here, and I'm going to define what we call the p-value. Yeah, we have a question.
Yes. So why are you going to accuse him of cheating while it is a 50% check? How can he cheat when it's 50%?
So we're not saying we understand what's going on. We're just saying looking at the data alone, it seems to suggest that something is going on here. Okay? So I'm going to write this thing, a definition of the p-value, okay? And this is very important. You should try to memorize this definition of the p-value, okay? The p-value is the probability of observing our data or something more unusual if we assume that H0, that the null hypothesis is true. All right. So this is the definition of the p-value. Okay. So when we come to our conclusions, and we'll get into the math behind everything. So the conclusions are, if the p-value is tiny, is small, okay, this provides evidence against the null hypothesis. Okay. Or in other words, remember the p-value is the probability of observing our data if we assume that the null hypothesis is true. So basically, if the p-value is small, what that's saying is if the null hypothesis is true, it is technically possible for us to observe our data, but it is highly unlikely. Therefore, I will conclude that the null hypothesis is not true. So write this down. All of this stuff is gonna feel uncomfortable at first, and my job is to try to get you guys to feel comfortable with these types of conclusions. Okay. So in our example, okay, with casino coin flip, I think that would actually be a silly game or a fun game. It's just like going to the roulette table and just putting it on red or black, right? Kind of. Okay, so casino coin flip, right? So the probability, so if someone is playing fairly, okay, so our null hypothesis will be the person is playing fairly. So his probability of winning is 0.5. Okay? And let's say the data show that he played 1,000 games and won 800 of them. Okay? So the p-value is equal to, if the p-value is equal to, what is the probability that a person playing the game fairly, because we're assuming that the null hypothesis is true, what's the probability that a person playing the game fairly will win 800 games out of 1,000? Okay, and I'm going to just do some quick math here. Actually, I'm going to use the computer to solve this thing. So I'm going to just ignore the computer code that I'm going to just type in here, but this is how I'm going to get my answer. Okay, well, it's just telling me that the probability is 0. But let me just see how many standard errors we end up away. Okay, 12.6 standard errors away. Let me just see. P norm 12.6. Okay. Okay, so we're ending up the computer, it's so close to 0 that the computer is just telling me 0. Okay, so technically it is possible for a person playing fairly to win 800 games out of 1,000. It might technically be possible, but the probability is probably something like 0.00000000. Okay, I don't know. We're essentially 12.6 standard errors away from the mean. Okay, so that's like 1 in a trillion, or 1 in or even more than that. Okay, just a bunch of zeros. It doesn't. You're more likely to win the lottery 3 days in a row than this to happen. Okay, is essentially what the computer is saying. Okay. So we could believe, okay, well maybe this guy is just really lucky. If he played the lottery 3 days in a row, he would have won 3 times. Or my initial assumption about him playing fairly is wrong. Okay, that the probability of winning is not 0.5. Something is going on. Maybe he's not being shady, but maybe the dealer is messing up or something is happening. Okay. So the probability of this happening by just random chance alone is so incredibly small that we're going to come to the conclusion that our initial assumption is wrong. Does that chain of thought make sense? Are we okay with that? Yes.
What's the cutoff where you'd say it's
Yeah. We'll talk about that. Okay. Yes.
Where did the C come from? The 12.6?
I just did some quick math on the computer.
All right.
Okay. So you don't worry about this just yet. Okay. So basically, we are saying technically. It is possible for a person playing fairly to win 800 games out of 1,000. Okay. But it is so incredibly unlikely that I will reject my initial assumption that he's playing fairly. Okay, so this is the thought process that we are using in hypothesis testing. Okay. So that's one possible conclusion, and then the other possible conclusion is that the p-value is large. So let me just copy this part up here. So again, try to really learn this definition of the p-value. Okay, so another possible conclusion is that the p-value is large, okay? And that means that if the null hypothesis is true, there is a significant probability of us observing our data, from random chance alone. Okay. So in this case, it doesn't prove this does not prove that the null hypothesis is true, but it does not provide evidence that the null hypothesis is false. Okay. So as you know, this week when you guys do your homework, really study these pages in your notes about how the p-value relates to the conclusion that you're making, and make sure you understand the thought process that goes in. Okay, you're going to do a lot of work that involves calculations and finding this and finding that, and those are important, yes, but the conclusions that you make, this is the important stuff. Okay, it's how we can relate, because what is statistics all about? It's about making conclusions from limited data. Okay, and so yes, there is a process with the math, and we're going to get into that, but the conclusions, the appropriate conclusions to make, that's the important thing. So make sure this thought process makes sense to you. Okay, so in our example, so casino coin flip example, how this works is the null hypothesis is that the person is playing fairly, so his probability of winning is equal to 0.5. And let's say our data in this case is he played 10 games and won 8 of them. So let me just do a quick math. That's actually pretty small. Let's say he wins, oh, I'm sorry, 7. Yeah, 5%, 0.054. So his p-value is equal to 0.054. I think 546 or something, okay? So what this says is that, okay, winning 8 games out of 10 doesn't happen very often, okay? So if a person plays fairly, okay, winning 8 games out of 10 will happen about 5% of the time, happen about 5.5% of the time. Okay? And so we can say this person is cheating, but probably, you don't want to anger your patrons at the casino. So it's probably better to give this guy the benefit of the doubt. Okay? Does it prove that he's playing fairly? No. He could actually be cheating. He could be doing something, and that's why he won 8 games out of 10. But a regular Joe Schmo who is playing fairly will still win 8 games out of 10 about 5.5% of the time. So it's not everyone's going to win 8 out of 10 games, but about 5.5% of fair customers will win 8 games out of 10, and they'll go home and they'll say, "Oh man, I had a great weekend at Vegas because I won 8 games out of 10 or something," you know. So that's how this goes. Okay, so this does not prove that the null hypothesis is true. Okay, it doesn't prove that he is playing fairly. Okay, but 5.5% of fair customers will win 8 out of 10 games. So we are not ready to accuse him of cheating based on this alone. Okay. Does that make sense? So read through these notes. We'll take a break here for 10 minutes, and we'll go through the actual math and the steps behind all this in chapter 8.